so this problem gives us two wires that are parallel to each other. They're 10 centimeters apart. So the distance from wire number 1 to wire number 2 is 0.1 meter. That's 10 centimeter. And what they want us to do, they say if the currents are in the same direction, find the force per unit length. Well, what's this going to come out as? This is going to come out as Newton per meter. So let's just go ahead and say, let's just say that both wires here are 1 meter, okay? And if you wanted to, you could say 2 meters and you get the exact same answer. It doesn't matter. Let's just say that the wires are 1 meter long because they want force per unit length. Now, the way to solve this problem is you have to pick one of the wires to be the source of the magnetic field. This problem has both of the major ideas from chapter 19 in the problem. Major idea number 1 is that moving charged particles in a magnetic field get a force, and then major idea number 2 is moving charged particles create a magnetic field. So here's what I'm going to do. I'm going to say that wire number 1 is the source of the B field. This is the source of the B field. Now, could I have made wire number 2 the source of the B field? Totally. I could have, but I didn't. So now, if wire number 1 is the source of the B field, what's going to be happening to wire number 2? Well, wire number 2 is sitting over here in the magnetic field created by wire number 1. Does that make sense? So first of all, let's identify which way is the magnetic field around wire number 1. So you got to use right-hand rule number 2. So stick your thumb in the direction of the current. So on this side of wire number 1, the magnetic field's going in, and then on this side of wire number 1, the magnetic field's coming out. So wire number 2 is sitting, so these X's here represent the magnetic field from wire number 1. Does that make sense? Wire number 1 is the source of the magnetic field. Now, which way is the force on wire number 2 going to be? So now you got to do right-hand rule number 1. So stick your 4 fingers in the direction of the magnetic field, right? So we're focusing on wire number 2 here. The magnetic field's going in, current is up. Which way is the palm of our hand? To the left. The force is this way, right? Now, dudes, let's reverse this and make wire number 2 the source of the magnetic field. Let's just do the same thing again real quick. Now, wire number 2 is the source of the magnetic field. So the magnetic field's going like this. On this side, it's dots, right? Wire number 2 is the source, and this side would be X's, right, like this. Okay, so wire number 1, the magnetic field's coming out of the page. Current is up. Which way is the palm of our hand? To the right. So what's the answer to this question? Are the wires attracted or repelled by each other? They're attracted. So the way you figure it out is you first got to say wire number 1 is the source of the magnetic field. Wire number 2 is going to get a force from that magnetic field. Figure out which way the force is, and then switch them. Make wire number 2 the source of the magnetic field, and then wire number 1 gets a force. You guys follow this? Okay, so now let's do the calculation part. How would you go about calculating an answer? So let's revert. Okay, so wire number 1, we'll make this guy the source. This guy's the source of the B field. So the magnetic field's going like this. It's going in on this side and then out on this side. Okay? First thing we have to do, guys, we need to find the strength of the magnetic field 0.1 meters from the source. How can we find out the strength of the magnetic field 0.1 meters from the source. B equals mu naught I over 2 pi r. So you plug into this. Mu naught is 1.26 times 10 Tesla meter over amp. The current is 10 amps, 2 pi 0.1. Okay, so the magnetic field comes out as 2 times 10 to the negative fifth Tesla. All right, now, how can we find out the force? So this guy, wire number 2 is sitting in the magnetic field created by wire number 1. So how can we find this force? F equals BIL, which is the equation for the force on a wire in a magnetic field. Okay, so this is where we're going to go. F equals, so B, this is 2 times 10 to the negative fifth Tesla. The current in wire number 2 is 10 amps. And then the length we said was 1 meter. Okay? And then what's the theta? What's the angle between the wire and the magnetic field? 90. Sine of 90 is 1. So this comes out as 2 times 10 to the negative fourth newtons. But how long did we say the wire was? Meters. So this is force per length. It's that much force per length of wire, per meter of wire. And that'll be the answer to part B. But guess what? For part B, the currents are running in opposite directions. If the currents are running in opposite directions, how is that going to change the problem? It changes the direction of the force. Right? So now let's have the current here going that way. Have the current running down. So let's see, so if he's the source, then the force on this wire is going to be that way. And then the force on this wire is going to be that way when he's the source. So dude, it's kind of definitely more of a tricky problem. The way to do it though, and I think I'm being super repetitive, one of the wires has to be the source of the field. The other wire is experiencing the force from that magnetic field.